Hi, this is Dr. Sweeney, and what we're doing here is we're working on some differential equations, and we're looking at how do I determine what kind of differential equation that I'm looking at, and then how am I going to end up solving it. So what I have here is I have this differential equation, and on first glance, it looks a lot like it might be exact. Okay, it might be an exact differential equation. So what I'm going to do is I want to check to see if it's exact. Okay, so I'm going to check to see if it's exact. Check for exactness. All right, so that means I'm going to take d dy of 2xy squared minus 3x cubed and d dx of negative 2y cubed minus x plus x squared y. Okay. Now, d dy of 2xy squared is going to end up giving me 4xy. Okay. And d dx of negative 2y cubed plus xy squared is going to equal 2xy. So what you want to notice here is they are not equal. Not equal. So I have some choices that I might actually be able to make. I could see whether or not I could actually work with an integrating factor, right? I could find an integrating factor, but I don't know. I have an instinct. What this also kind of looks like and reminds me of is it also reminds me of a, um, a homogeneous to degree zero problem, okay? But one in which I might have to make some adaptation. So I've got now 2xy squared minus 3x cubed dy equals, okay, if I just move the other side, 2y cubed minus x squared y over dx, excuse me, okay? And the reason why I'm looking at this is I noticed that my highest degree for x is x cubed, my highest degree for y is y cubed, okay? So that might actually indicate to me that I might, in fact, be able to divide by some power of x to to allow me to do some change of variables. So that actually is kind of a handy thing to do. So let's see. Let's see what we got. So if I divide out, so I'm going to end up with dy, right, equals 2y cubed minus x squared y over 2xy squared, excuse me, 2xy squared minus 3x cubed dx. And so consequently dy dx is going to equal 2y cubed minus x squared y over 2xy squared minus 3x cubed. All right? Now, if it is homogeneous to degree 0, then I should be able to divide both the top and bottom by x cubed and end up with a function of y over x. So let's see if that's the case. Okay? So I'm going to take this dy dx, and I'm going to set it equal to 2y cubed minus x squared y, okay, times 1 over x cubed, and then 2xy squared minus 3x cubed divided by 1 over x cubed. Okay? And this is going to equal 2 y cubed over x cubed minus y over x divided by 2 y squared over x squared minus 3. Okay? Which will end up equaling 2v minus, or excuse me, 2, change to v yet, 2y over x cubed minus y over x divided by 2 times y over x squared minus 3, which now what we can do is we're going to let v equal y over x, and that means vx equals y. And so when we do that substitution, I'm going to end up with dy dx is equal to 2v cubed minus v all over 2v squared minus 3. And notice that because I can write it as a function of y over x, this is in fact homogeneous to degree 0, and I can use change of variable. Okay, awesome. So Now what I have is I'm going to have to make this substitution. I have to figure out what dy dx is. So I'm going to use this to figure out what dy dx is. So dy dx is going to equal dv dx times x plus v. Okay, and that we just used implicit differentiation in order to give us that. Okay, so now I have dv dx times x plus 2v cubed minus v over 2v squared minus 3. Okay, I'll subtract out my v. All right, so we now have dv dx times x equals 2v cubed minus v all over 2v squared minus 3 minus v, which equals 2v cubed minus v all over 2v squared minus 3 minus v times 2v squared minus 3 all over 2v squared minus 3, which equals 2v cubed minus 2v cubed. I'm just switching things around right now. Minus v plus 3v all over 2v squared minus 3. Okay? Which equals now 2v over 2v squared minus 3. I'm just going to go in here, make sure that I have everything copied down correctly as I'm working. All right, looks good to me. Excellent. Okay, so now what I have is I have this differential equation, dv dx times x equals 2v over 2v squared minus 3, which is definitely separable. Okay, one of the great things about doing change of variables is that we end up with a separable differential equation. So, with just a little magic, I'm going to end up with 2v squared minus 3 over 2v, okay, equal dv equals dx over x. All right, fantastic. Okay, and so this then is going to be 2. So now that we have that, we're just going to need to integrate. So I want to integrate 2v squared minus 3 over 2v dv equals the integral of dx over x. Okay. And so this gives me, this equals the integral of v minus the integral of 3 over 2v, which equals, and we're just going to, this is going to end up being ln of x plus c, minus 3 halves ln of v, which equals ln of x plus c. Okay. Whew. All right. Now, let's just say that what I want to do is I just want to put this in. I'll figure it out implicitly. All right. So I just want to write it out implicitly. I'm going to have 1/2 times y over x squared minus 3 halves ln of y over x equals ln of x plus c. Okay. I could also, if I wanted to, what I could do is I could try and solve. But we'll leave that for another time. We'll actually just kind of finish this out, discuss, just kind of review what the process is for doing our change of variables. All right. Well, the first thing that I did, right, okay, is I went in and I checked for exactness because it looked like it might be exact. I was like, hey, that's kind of how they draw exact stuff. But it turned out it wasn't. And since it wasn't exact, I also noticed that my highest power of y and my highest power of x were both the same power. And so that kind of also indicated to me that maybe, just maybe, I might be looking at something where I could have change of variables. I had a homogeneous degree 0 differential equation. So what I did was I manipulated the differential equation to actually be put into the form where I can check for it to be homogeneous to degree 0. That is, dy dx equals some kind of rational function. And then, what did I do? I divided by the power of x, the greatest power that we have available, which in this case is x cubed. Okay. Then, to boot, once I did that, I now had a function in terms of y over x, and that confirmed that I was going to be looking at something that was homogeneous to degree 0. Okay, so that's what we ended up doing over here. And so what I do then is I do a change of variables. I'm going to make a substitution. I'm going to let v equal y over x and vx equal y. And so consequently, what I'm going to do then is I'm going to end up with this differential equation right here. Okay, and then I'm going to have to use implicit differentiation in order to figure out what dy dx is and make my substitution for dy dx. Once that's done, now what I have here is this thing here is a separable differential equation that I'm going to solve for v. So that's exactly what I did, right? I separated the variables, all right? And I determined from the separation of the variables that then I separated the variables and then I integrated. Once I was done with the integration, I basically wrote it in terms of y over x. Okay, so if I ask you to just keep it in terms of implicitly, then you can just leave it like that. If I say solve for y, then you're actually going to have to do some of the algebra. All right, so that kind of finishes up that kind of problem. A little bit tricky, but it kind of emphasizes something that's really important, and that is that you really should be thinking about what kind of differential equation am I looking at, and how do I know? All right, so that concludes this little lesson.